So this is the Huffman coding, which is a compression algorithm. It's also known as the greedy algorithm. So I want to see how we can compress this string, Mississippi River. There is a total of 17 characters. Let me confirm: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. If each is transmitted using 8-bit ASCII code, that'd be 132 bits. So I'm going to count the frequency here of each character. There's one M, there's 5, there is 4 S's, 2 P's, 1 R, 1 V, so 1 E and 1 blank. Now, 5 plus 1 is, so that's 10, 12, 13, 14, 15. Wait a second. This is 5 plus, how many S's are there? There are 4 S's. So this becomes 10, 12, 13, 14, 15, 16. I'm missing one more character. I need 17. The I's are 1, 2, 3, 4, 5 I's. There's one M. The S's are 4S. The P's are 2 P's. Okay, there's 2 P's. The R's are 2 R's. So there are 2 R's. That's where my problem was. So there are 2 R's. Okay, so let me put that together. So you got 2 R's. Okay. Now if I add these up, I get a total of 17 characters. That has to match. Good, we caught that. Okay. So now I'm going to put the lower ones on the right side. For instance, I'm going to put my blank here. There is only one blank. There is an E, that's always only one E. There is a V, that's only one V. There is an M, only one M. There is an R, there are 2 R's. There are 2 P's. There are 4 S's. And finally, there is 5 I's. Now, the way the Huffman code, Huffman tree works is that the characters that have the most frequency should should be represented using the least amount of bits. So let me combine the ones with similar frequency. So there's 1 here. So 1 plus 1, so that's E, and that's a blank. Okay, so I got one of them. M and V, so this would be 2MV. Now I should be able to combine this one, and this should be 4P and R. And you know what, I can combine these two. That should be okay. So this should be 9I and S. Now, these two are together, so I should be able to combine those. That's a 4M, V, E, and a blank. These two here should be able, or what I can do, combine these two. They're 4 and 4, so if I run these together, this is going to be 8. That's a P, R, M, V, E, blank. And finally, I can combine this. So that's my root. So this becomes 17 I, S, P, R, M, E, blank. So you see that? This is my tree. So this is my Huffman tree. So what's happened is, that's the root. The left side, we can assign them 0. The right 1, 0, 1, 0, 1, 0, 1. And this is 0, and that's a 1. This is 0, and that's a 1. This is, so it doesn't matter whether I do 1 or 0. I could switch these around. I could put 1 here and put 0 there. How do you represent this? Now, We start always from the root. We start at the root of the Huffman tree. So if I want to go to blank, I go 1, 1, 1, 1. So blank is represented as 1, 2, 3, 4. How about E? 1, 1, 1, 0. So E is represented as 1, 1, 1, 0. How about V? It's going to be 1, 1, 0, 1. V is 1, 1, 0, 1. M should be 1, 1, 0, 0. 1, 1, 0, 0. R is going to be 1, 0, 1. 1, 0, 1. How about P? 1, 0, 0. And then S is 0, 1. And I is 0. So as you can see, the ones with the most frequencies have less bits, less frequency, are represented using more bits. So now if I add these up, okay, I got 5 I's, 2 bits each, that's a 10. I get 4 S's, 2 bits S, that's 2 bits each, that's 8. 3 bits, that's 6. 2 times 3, right. And this is 2 times 3, that's also 6. This is 1 bit, one frequency, it's 4 bits. And this is 4 bits. And this is also 4 bits. And this is 4 bits. If I add these up, I am going to come up with, let's see, if I end up adding all these bits up, so that's going to be, let's see, I got 8, 18. So this is 18 here. Let's see what happens. So I got 18 here plus 20. That's 20. So I got, okay. So I got this is 18. Okay, 24. So if this is 24, that's 30, 38, 42, 46. So I got a 46. Okay, total bits. Now all I have to do is take a percentage of that. So for me to take a percentage, and I could look through this, and so I have, okay, let me find this out. Hold on once. Okay, so I got a total of 46 bits because I got a 10 plus 8 plus 8. Just want to confirm. Okay, so it's actually 10 plus 8 plus 6 plus 6 plus 4 plus 4 plus 4 plus 4. So that gives me a total of 46, and I take a percentage of, so I'm going to do 46 bits and take a percentage, so 46% of, so multiply that by 136 bits total, so that gives me 68%. So if I subtract that from 100, that's the savings. Now, how am I going to transmit this? For me to transmit this, I need to transmit the actual tree and the number of characters. So if you look back here, okay, 46%, let me take this out. M is represented as 1, 1, M is 1, 1, 0, 0. I is represented as 0, 0. S is represented as 0, 1. And P is represented as 1, 0, 0. And R is represented as 1, 0, 1. V is represented as 1, 1, 0, 1. And E is represented as 1, 1, 1, 0. And blank is 1, 1, 1, 1. So see, we got a total of 47 46 bits, you multiply this get transferred. So 46% of 136, 136 bits, that gives me 68%. Subtract that from 100, that's the savings. And this is known as the Huffman tree that we built. And the tree needs to be transmitted, the number of characters, what they represented, because then they can go backwards. So like to get I, you start from the root. Thank you for listening.